Lastly, for the application section of this lesson, what we're going to talk about is the point of diminishing returns. So this is the point at which the rate of change is going to go from increasing to decreasing. So remember, I'm going to think of this rate of change as being f prime. This is where f prime is going to go from increasing to decreasing. And saying that f prime is increasing is the same thing as saying that its derivative is positive. So that means that we're going from f double prime being positive to f double prime being negative. In other words, we're looking at an inflection point. Now, the point of diminishing returns will necessarily be a place where the rate of change has a local maximum value. That's because the rate of change went from increasing to decreasing. So this is a place where f prime is at its best. And there's a little note here that just says that money spent beyond that point can still increase sales, but it's not going to give you the same sort of bang for your buck. You are not going to get the same sort of rate as you were getting earlier. So if you're interested in maximizing the rate of change of your function f, then you should do that at this point of diminishing returns. So let's look at an example of this in problem 10. It says a national food service is running concessions and their research department chooses some particular football stadium, and it was found at this stadium that the demand for this new hot dog is given by p is equal to 8 minus 2 ln x for this particular x range. So this is the domain of the function that we're given. So we can ignore that for now, but just notice that this price function only applies if the x value that we're plugging in is between 5 and 50. And x is supposed to be the number of hot dogs in thousands that are being sold, and p is the price in dollars for the hot dog. So in part A, it just says find the local extrema for the revenue function. And for this, we can use the second derivative test that we just talked about. So if we're looking for the local extrema, notice first we're talking about the revenue function. So maybe it would be a good idea to first just write down the revenue function. The revenue function is equal to the quantity sold times the price that you sell them for. So that's quantity times price. And that would be x, because we sell x hot dogs, or really x thousand hot dogs, times the price. The price was given to us in the prompt as 8 minus 2 ln x. So that's the revenue function. And if we wanted to compute the local extrema for this, then what we would need to do is we would need to compute r prime and r double prime. So you could distribute the x here in r and then take a derivative, but just to practice using some of our rules, let's use the product rule here. So I'm going to think of r as being a product between these two things, and we'll use the product rule to compute this derivative. So r prime is going to be the first thing times the derivative of the second, so that would be x times the derivative of the thing in parentheses. Now the derivative of 8 is 0, and the derivative of negative 2 ln x will be a negative 2 times 1 over x, because the derivative of ln x is 1 over x. So that's first times the derivative of the second, plus the second term times the derivative of the first. So here's the second term, or really I should say the second factor, times the derivative of the first thing, but the first thing out here is just x, so its derivative would be 1. So this is what we get as r prime. We can clean this up a little bit. So notice that in this first term, we have a factor of x and a factor of 1 over x. So you could cancel those to just get a negative 2. And then this last stuff just becomes a plus 8 minus 2 ln x. And then lastly, just to clean this up by combining like terms, what we get is a 6 minus 2 ln x. So this is r prime. Now, if we're trying to find the local extrema, that means that our first step is to find the critical points. A critical point is where r prime is equal to 0. So if we're looking for the critical points, we want r prime to equal 0. So we're just going to take r prime, which is this, and set it equal to 0. And then we can solve for x to find the critical points. So if I add 2 ln x to both sides, I get 6 is equal to 2 ln x. Dividing both sides by 2, I get 3 is equal to ln x. and then applying e to the x to both sides of this equation, or in other words, exponentiating with base e on both sides, I get e cubed is equal to x. So this is our critical point. E cubed is the only critical point. And now we can apply the second derivative test to decide whether this critical point is a local max, a local min, or neither. Now to apply the second derivative test, we first need to just compute the second derivative. So I'm going to take this r prime value that we found a second ago and take its derivative to find r double prime. So if I take a derivative of this circled expression, the derivative of 6 would be 0, and as we have already seen, the derivative of negative 2 ln x would just be a negative 2 times 1 over x. So that's r double prime. And now to apply the second derivative test, I just take that second derivative and plug in the critical point that we found a second ago. So I want r double prime evaluated at e cubed. That would be negative 2 times 1 over e cubed. And you could plug this into a calculator if you wanted to, but again, we don't really care what the value of this expression is. We just care about whether it's positive or negative so that we can determine the concavity. And in this case, it's clear that this is a negative number, whatever it is. So that means we're looking at a place where we have a negative concavity, or a downward concavity. So this critical point, e cubed, will be at a place for r where there's a negative concavity, and that means we're looking at a critical point with negative concavity like this. And therefore, e cubed is going to represent a local max. So I'll just write that as local max at x equals e cubed. Okay, so now we found the local extrema that we were looking for. And then in part B it says, on which intervals is the graph of this revenue function concave upward or concave downward? So notice here we're looking for the concavity. We want to know when the revenue function r is concave up or concave down. So that's the same thing as asking about the sign of r double prime. And r double prime, as we saw above, is negative 2 over x, or negative 2 times 1 over x. So we just want to know when this is concave, or sorry, when this is positive or negative in order to determine when this revenue function is concave up or concave down. But remember, if I just scroll up a little bit, remember that this price function is only defined whenever you have x between 5 and 50. So the domain of the revenue function is just between 5 and 50. And that's important because if we're looking at r double prime, it will inherit the same domain. So we're still looking at an x range between 5 and 50, because that's the only time that we were able to apply that price function. But if you plug in any x value that lives between 5 and 50, notice you're always plugging in a positive x value. So this would be a negative 2 divided by a positive number. So this means that r double prime is less than 0 for all x. Maybe I should say between 5 and 50. So you could write your answer like that, or it would also be okay to just say that r is always concave down. That's because its second derivative is negative on the entire domain. So lastly, let's look at this example. I think this example will illustrate what this point of diminishing returns actually means. So let's look at 11. So this discount appliance store is selling 200 large screen TVs monthly. If the store invests X thousand dollars into an advertising campaign, the ad company estimates that the monthly sales will be given by this function, where X is between 0 and 12. When is the rate of change of sales increasing and when is it decreasing? So we want to know when N prime is increasing or decreasing. N prime would be increasing when its derivative is positive. So n prime is increasing whenever n double prime is positive, and n prime will be decreasing whenever its derivative is negative. So we're looking for when is n double prime positive and when is n double prime negative. And then the next question is, what is the point of diminishing returns, and what is the maximum rate of change of sales? And then we'll graph n and n prime on the same coordinate system. I wouldn't ask you to do this one by hand. I just wanted to supply the graph below so that we could look at it. So don't worry about the graphing for now. For now, let's just worry about answering these first few questions. So the first few questions were, when is n double prime positive? When is n double prime negative? What's the point of diminishing returns, which will be the inflection point? And what is the maximum rate of change of the sales? Okay, so let's start by just computing these derivatives. So when we compute n prime, we're just going to use the power rule a few times. So this would be a 12x squared minus x cubed for that first derivative. And then n double prime is going to be a 24x minus a 3x squared. Now we do care about when this is positive or when this is negative, so I'm going to do the usual thing where I sort of rearrange this and factor it. You don't necessarily have to take exactly the same steps, but I like to write this polynomial in standard form so that it has descending degrees like we normally do. And then I'll factor out any common factors that we have. I notice that negative 3x is a common factor, so I can factor that out. If I take that away from the first term, I get an x, and if I take it away from the second term, I get a minus 8. So this is n double prime. And from here, it's easy to see what the zeros are for n double prime. We see that n double prime is 0 if you plug in x equals 0, and it's also 0 if you plug in x equals 8. N double prime is also a quadratic that opens down because its leading coefficient is negative. So if you remember how to graph quadratics, the graph of n double prime will look like this. It'll have a root at 0 and it'll have a root at 8. And n double prime will be positive between 0 and 8, and it'll be negative thereafter. But you could also determine the same information by making a little sign chart for n double prime if you wanted to. We just found the two inflection points at 0 and 8. And you could plug in specific values in each of these subintervals to see that n double prime is negative and then positive and then negative. So if you prefer using this little sign chart method, that's fine. But you should remember, well, you should have at least at some point seen how to graph quadratics. And that can help when doing some of these problems. So let's answer the first set of questions here. We wanted to know, when is the rate of change increasing and when is it decreasing? So rate of change is going to be increasing on the interval between 0 and 8, because that's where the second derivative is positive. So that will be this region here, where the second derivative is positive. The rate of change in sales is decreasing whenever whenever n double prime is negative. And that's whenever x is between 8 and 12. So notice that again we have a restricted domain. Our domain is only with x values between 0 and 12. So I would say that this is decreasing on the interval from 8 to 12. And I don't care whether you include the endpoints here. So if you'd prefer to write these as open parens rather than closed, that's fine. So that answers the question of where the rate of change is increasing or decreasing. Next, we wanted to know, what is the point of diminishing returns? Remember, the point of diminishing returns is when the rate of change goes from increasing to decreasing, and that happens at 8. So this is where the rate of change goes from increasing to decreasing, or where n double prime goes from positive to negative. So the point of diminishing returns is x equals 8. And remember that the point of diminishing returns is also where the maximum rate of change happens. So if you wanted to know the maximum rate of change, you can take that point of diminishing returns and plug it into the rate of change. So in other words, I can plug in this x equals 8 into n prime, the rate of change, to get the maximum rate of change. So if I take n prime and evaluate it at 8, that will be 12 times 8 squared. So I'm just taking this n prime up here. 12 times 8 squared minus 8 cubed. And this ends up being 256. If you were curious in that previous video where I got the 256 from, I knew it was one of the answers that showed up at some point in these videos. I just didn't get the problem right. So this is something you could just plug into a calculator, but what we end up getting is a maximum rate of change of 256. And remember, the units for a rate of change will be the units for the original variable n. So that would be in terms of sales, divided by the units for x, and that was in terms of thousands of dollars. So this means that the best bang for your buck that you could get would be 256 sales per $1,000 that you spend. After this point, you'll start getting more sales still, so if you continued to spend on advertising, you would continue to increase your sales, but you wouldn't get 256 sales per $1,000 that you spend, you would get a little bit less. So your money is not being quite as effective. And you can see that from the graph down here at the bottom. So remember, n is supposed to represent the total sales. N does continue to rise as we go. So it makes sense that as you spend more and more advertising money, your sales do continue to rise. But notice that if you were just concerned with the number of sales per advertising dollar, we do hit a point of diminishing returns here at about 8. That's also the inflection point for the original graph here. So the best rate that you could get would be this 256 sales per $1,000 that you spend. After this point, you're not getting quite as good a return on your advertising money, but you are still increasing your sales. So that's what a point of diminishing